Hey, folks, welcome back to EarthSky. And we've finally got Leonard Ohenhen in here in the studio for a recording. And he is the man who is sounding the alarm about sinking U.S. cities. He is the author of a study that says, well, you know what? I'm going to let him tell us what it says. Let's get him out here. Leonard, welcome. Finally, welcome to the show.
Yeah, thank you so much, Dave.
No, thank you. Thank you for being here, and thank you for your persistence. So you have a paper. You and your team rather have a paper out that tells us that. Oh, I'm sorry, I didn't tell people who you are. You were a geophysicist at Columbia University, and more specifically at the is it the climate? Tell us where you are.
So yeah, I'm associated with the Lamont Doherty Earth Observatory at the Climate School in Columbia University.
Right. Okay. And you and your fellows, you study the Earth and the effects of climate change there. Okay. So let's move on. You and the team, latest publication of which you are the lead author. Last month came out in Nature Cities. It's journals, peer reviewed, the whole thing. But it's a bit alarming. You're telling us that 28 major U.S. cities are sinking, and we've got a map. So let's take a look at this and which cities are sinking and how much sinking are we discussing here? What do we got?
Yeah, the result is striking, and for two reasons. One, sinking is a phenomenon which is often not discussed, particularly as it relates to coastal risks. And so a lot of people understand climate change and sea level rise and its effect on the environment. Often land subsidence or sinking of the land is underappreciated. And in this study, we wanted to look at not just the coastal cities, but every major US city with a population over 600,000. And then we explored the cities using satellite data and found what the rate of sinking is in all of the cities. And we found that on average, the cities are sinking between 1 to 5 millimeter per year. So that is an annual rate of 1 to 5 millimeter per year. And so in this figure you're showing here, the colors of between yellow to reddish, as you have from places like in Las Vegas or in places like Houston and Dallas. Those are all locations where the cities are sinking on average at the different ranges of 1 to 5 millimeter per year. But you also have places where the land is rising, which are the places where you have the green color. So in those cities, San Jose, Jacksonville, and in Memphis, those cities are experiencing uplift of between 0 and 1 millimeter per year. But the data set that we get is not just a single value per city to say the entire city is sinking at this rate. But what is really good about the satellite measurements that we obtain in this study is we have especially varying rates. And so we have places in Houston, for example, where we see rates of greater than 1 centimeter per year. And in almost every city, we see those type of rates where even if the average rate in the city is 1 millimeter per year, you have places that are sinking up to 1 centimeter per year, which is a really, really astounding rate of sinking when you compare it to sea level rise, for example.
It sure is. It sure is. So all the cities, you say, have at an area somewhere in that urban area that is sinking 1 centimeter per year. So why should the people who are living in these areas why should they be aware of this? Let me say this. The paper says that the sinking cities have adverse environmental and socioeconomic consequences worldwide. Should people be concerned about that? Tell us why, if they should, why they should be.
Absolutely. Well, for me, subsidence is not just a geophysical curiosity, like something that you need to study for the sake of studying it. It has real escalating human consequences. When cities sink, they become more exposed to flooding. And this is not just cities that are on the coast, but also every urban city. And so during rainfall, we refer to this as pluvial flooding. flooding that occurs during periods of high precipitation, for example. Places that are sinking are often more exposed to these floodings as a result of this. But you also have low-lying neighborhoods that once drained properly that may now sit below flood threshold or below high tides, which are often coastal cities. And the most damaging aspect of subsidence, which is often not discussed, is the slow, often invisible aspect that compromises infrastructure systems over time. And this results not just from the sinking alone, but from differential subsidence. So what happens when you have different sinking in different aspects of an infrastructure? So a road, a levee, or a building are sinking at different rates, or even when you have sinking and rising on different parts of the infrastructure, that can compromise the infrastructure slowly over time, that become only manifest when you start seeing more visible signs like cracking on even pavements, or sometimes even the fatal collapse of a building.
So once you actually see the cracking and it becomes obvious to the eye, the damage is done at that point, isn't it?
Yes, exactly. So you have more costly repairs as to what you would expect when you don't have the visible signs.
So let's see. Some more quotes I've got here for you. Well, you know what? You do tell us the main reason. Let's go there first. Let's go there. You tell us in the paper why you and your team think that's happening. And this is the map
Yeah.
you wanted to discuss while we talked about that. So give us a walkthrough on this and tell us what's happening here.
Yeah, so generally, the causes of subsidence globally is divided into two. We have natural processes and anthropogenic processes. And so the natural processes will be things that are driven naturally or that occur over time. For example, in most coastal areas, they are underlain by what we refer to as geologically as young sediments. So most recently deposited during the Holocene period. And so they still undergo compaction over time. And that means they settle slowly over time. With or without any humans, you would have those compaction over time in majority of the coastal areas that we have. But human activity often accelerates this rate in most of these coastal regions. And that has to do with extraction of resources. So oil and gas or groundwater extraction from aquifers would cause the ground to sink more than they would under natural conditions. But you also have another natural process, which is referred to as glacial isostatic adjustment. And this has to do with a long-term geological process where the land is still slowly sinking in response to the melting of massive ice sheets from the last glacial period. And so a simple way to think about this is you have a memory foam and you put a weight on the memory foam. You would have that area where you have that weight go down, and areas adjacent to where you have the weight would go up in response to that. So think of the ice sheet as that memory, as that weight that you've put on the memory foam, and now the Earth is the memory foam. But what happens when you take off that weight? Well, the areas that went down due to that weight starts coming up, right? And that is what is happening on areas where you have the greens and the purple on this map here. In Canada and the rest, they are undergoing uplift or rebound going upwards because of that weight of the ice sheet. But in other areas in the United States that are all yellow and red on this map, are places that were once up that are now sinking slowly as a result of that weight that has been removed. And so we have those glacial isostatic adjustment. And from this color, you could see that in the majority of the cities around the region of the Great Lakes, and also in some parts of New York, Washington, Columbus, Detroit, Chicago, Indianapolis, Nashville, and Denver, the average rate you have for those cities, which are the colors of the circles, are exactly the same as what you have as the background GI effect. What that means is that those cities are sinking as a result broadly because of glacial isostatic adjustments. But in other places, like in Houston, for example, Fort Worth, Dallas, and in San Diego, those cities are sinking because of the extraction of resources. You could see in Houston, Fort Worth, and Dallas, for example, how the colors are so much redder than what you have in the background, which is the light yellow color. And that is because you have such a high rate of subsidence in those places.
Okay, that's concerning. So to sum up quickly, there are a number of causes at work, man-made and natural. And can you tell? Can we assign numbers? How much of this is man-made versus natural occurrence from geological processes? Do we know?
Well, yeah, we can. Like I mentioned, in Detroit, Columbus, Indianapolis, and Nashville, we could say almost 100% of the average rate we measure are due to the natural process of glacial static adjustment. In places like Washington, you have a more flexible contribution. You have a lot of the process is due to glacial static adjustment, but you still have localized impacts due to that natural settlement or compaction of the sediment. And you could also have extraction of resources in some places, which is why the spatial map that shows the extent of sinking or the rates of subsidence in the cities is very important, because you can have not just the average rate, but you can see localized places in the city where you have extraction resources as the driver, for example, or the reclaimed lands, for example, that are subsiding in some cities.
You know what you mentioned now that, and you mentioned earlier that in some of these areas, in fact, in all of these urban areas, you said at least part of, let's go over to this next map. Part of every one of these urban areas is sinking by at least 1 centimeter per year. And here's some more quotes. I was going to mention these earlier. We estimate that at least 20% of the urban area is sinking in all cities, affecting approximately 34 million people. Roughly around 9 to 10% of the U.S. population. When you say cities are sinking, we're not talking about entire cities necessarily, but some cases we are. And I saw in the paper rather, that it's worse in Chicago, Detroit, Houston, and New York. What do those places have in common? Let's talk about that. What's going on there?
Yeah, well, interestingly, they don't all share the same driver of subsidence, and so they're not driven by the same process, like we mentioned earlier. And so in some places, the rate of sinking differs in some of these different cities, and so the driver also differ. In New York, we have a lot of glacial static adjustment. In Houston, for example, on this map, you have a lot of resource extraction, so groundwater use as the major driver of subsidence. And so they're all different for the different cities. But what they do have in common is large populations and infrastructure and high exposure to these environmental hazards, which is why understanding the local cause of subsidence is so important for us to design city-specific effective responses for the different cities.
Okay, and we did talk about that. We mentioned that, in fact, the paper says that there are more than 29,000 buildings located in high and very high damage risk area. We talked about that process of shifting infrastructure causing this damage to occur. That stuff doesn't flex very well. Our coastal cities, I don't think we covered that. Coastal cities, are they or are they not more at risk to these processes? And what can we do? I mean, the whole point of your study is to warn us so that we can get ahead of the problem. What can we do about it? Are coastal cities more at risk? And what do we do? Sorry about that. They want to.
Yeah. So, firstly, about coastal cities being more at risk, the answer is yes. And this is because they have amplified risk because subsidence compounds sea level rise. And so every city has that hazard to infrastructure, because coastal cities also have infrastructure in them. But coastal cities have the added burden of facing multiple flooding events. So they have flooding when it rains. You have flooding from hurricanes, for example, and you also have the future effects of sea level rise that keeps increasing slowly. And so subsidence compounds sea level rise in itself, leading to relative sea level rise, but it also reduces the effectiveness of levees and flood defenses that are put in place in some of these places. It increases the frequency of nuisance flooding, And also it shortens the timeline for critical adaptation. And so if you have a future scenario plan for sea level rise, and say sea level rise would be 1 meter by 2050. With subsidence, it now becomes even more than 1 meter, because you have the dual effect of sinking land and rising seas. And about what we can do about this, that was the whole point of the study. It's not just to sound the alarm and say there's a threat and then go on our merry way. And it's also a really important aspect of the study that we try to do at the conclusion of the study, to say subsidence is not inevitable. We can do something about it. But first, we can't provide a solution for what we cannot measure, which is why knowing how much the city is sinking, what part of the city are sinking, what is the cause of the city sinking, is a major aspect of understanding what we can do to stop it. And so, for example, in cities where groundwater extraction is the primary cause, we can transition into surface water as an alternative resource for the city, for example. So in the map of Houston, you see areas where the subsidence were really, really red. That shows high subsidence. So those are all areas where subsidence exceeds 1 centimeter per year. But you also see areas towards the coast on the southeastern parts that are greens and yellow. Here, the rate of vertical land motion is stable, almost at 0. And this is because Houston has implemented adaptation resource extraction policies in some of those areas. And so it does work. There is mitigation that can be done to shift cities from rapidly sinking areas into less even stable or even uplifting areas in some of these cities. And so there are development plans that can be put in place, but also where subsidence cannot be mitigated, we can also adapt to it. So if you know how much a city is sinking, for example, and that it has effects on infrastructure, then you can design built-in codes in the various cities that can help respond to the city and help avert negative consequences for infrastructure.
Okay, so it sounds to me like there are definitely solutions we can employ as long as we're willing to act and we have the knowledge that people like you are providing. So let me thank you for that. Let me thank you for doing the study and ringing that alarm bell, sounding the alarm, because it's a real threat to our infrastructure. Leonard, do me a favor, hang around backstage. I want to tell these people thank you just a minute. In fact, why don't you can just hang out here and I'll tell everybody thank you so much for joining us today. We have an important message.
Thank you for having me.
Yeah. And thank the viewers. I want to thank the viewers. Thank you guys for being here. Had an important message. I'd like you to like and subscribe, please. And we are here every weekday at the same time. That's 1715 Universal Time Coordinate. So come on over and visit us at earthsky.org. Leonard, I'm gonna put you backstage and tell these people that there's one Earth, one sky, EarthSky, and I'll see you next time, which is gonna be, actually, let's check that out. We have Dan Garisto. The topic is frozen science research grants and what that might cause for the U.S. science community. It's an important topic again. Come and check it out. We'll see you then. Thank you so much. Bye-bye, folks.